differentiation of omega with respect to time t, so we get it as omega back again. So C into V naught into omega into cos omega t. In non-alternating current concepts and all, you have V is equal to I into R. So V by I is equal to R. What is the behavior of the resistance? It is giving the opposition to the flow of current. The voltage is lagged behind, but the current is forward. It is moving forward, that is plus 90 degree ahead than that of the voltage. That is why we draw this in negative axis. So we have VC. Hello everyone, I am Brinda, Faculty of Physics from Vidhyaashram Pre-University College, Mysuru, welcoming you all to session 4 of chapter 7, Alternating Current. So in today's class, we are going to deal with alternating voltage applied to a capacitor. First of all, in the previous class, we have studied about the alternating voltage applied to an inductor. Now exactly we study about the capacitor. So how is the capacitor represented? It is in this form. Okay, so now two parallel lines which represents the capacitor. So when an alternating voltage is applied to a capacitor, which means to say that we are connecting the AC source to the capacitor over here, for which we know that the voltage what is represented with respect to the alternating voltage is V is equal to V naught sine omega t, where V is the instantaneous value of the voltage and V naught is said to be the peak value of the voltage, omega is said to be the angular frequency, and t is the respective time which is with respect to the alternating voltage applied to a capacitor. So with the help of this, we need to check up, that is this, consider this as a equation 1. So we know that V is equal to Q divided by C equation, that is voltage is equal to the charge per unit capacitance of a capacitor is said to be the voltage. Okay, so when you have this, or a capacitance is nothing but the charge per unit voltage is said to be the capacitance. So two can be interchanged. So we have the equation as V is equal to Q by C. So we have Q is equal to V into C. So representing for V, we have C into V naught sine omega t is the equation what we have. Consider this as equation 2. Okay, so we have equation 1 in our hands and equation 2 in our hands. And we also know that the current I is equal to, we have to find out by applying alternate voltage applying to a capacitor, we need to find out what is the instantaneous value. If you have the instantaneous value of voltage, what can be the instantaneous value of the current is what we have to identify by this derivation, for which you have to give the I. It is always whenever the alternating voltage is applied to resistor, inductor or capacitor, whatever might be the situations or the circumstances, the only thing what we check is how exactly the voltage and I react with respect to each other. So now we have I is equal to, we know that change in charge with respect to time is said to be the I, current. Okay, so for this we just apply I is equal to D of, instead of Q I substitute C V naught sine omega t divided by dt. With respect to dt, you are deriving C V naught sine omega t, differentiating it. So I is equal to, C can be taken outside, so dv naught sine omega t by dt will be the thing. So we have I is equal to C into V naught into cos omega t. Omega is what we have to differentiate with respect to t, because omega and t are the one which occurs in pairs. So something with respect to that differential equation with respect to what we derive will be t, differentiation with respect to time. So differentiation of omega with respect to time t, so we get it as omega back again. So C into V naught into omega into cos omega t, and you have this equation. So we also know that cos omega t, from the previous session you will get to know the allied angles trigonometric functions. We have sine pi by 2 plus omega t will be the equation, or else even you can write it as omega t plus pi by 2. So I is equal to V naught into C into omega, cos omega t will be sine omega t plus pi by 2 will be the equation. So this is of the form I naught. I can even write it as I is equal to I naught sine omega t plus pi by 2. So here we have I is equal to I naught sine omega t. I is equal to I naught sine omega t. This is same as this one what is considered over here. Okay, V is equal to V naught sine omega t. But here I is equal to I naught sine omega t, which means to say plus pi by 2. Pi by 2 value is nothing but 90 degree, for which we can say that the current leads voltage by 90 degree. So here the current is said to be leading. Current leads voltage by 90 degree is, or it is also called as pi by 2, is what we are studying under this concept, alternating voltage applied to a capacitor, for which you just give a leading waveform. For that you have a waveform diagram which is given by so this is 0, this is pi, this is 2 pi, this is 3 pi. So this is a waveform diagram which represents the phase, that is omega, and this is the representation of amplitude. So this is the voltage curve, and now we draw the current curve. It leads by pi by 2, so it has to come and reach the center pi by 2 from here. Okay, and then it starts flowing in the same manner. So here it is pi by 2, 3 pi by 2, 5 pi by 2 is the values under this. So this is a waveform diagram. So this is the representation of current and this is the representation of voltage. And next we have a phasor diagram which is given as, phasor diagram means a diagram which represents its directions. It is a vector quantity. So now when you draw the phasor diagram, you will have to have this axis, and from here you just draw the voltage is represented here, and the current is leading voltage by pi by 2. Leading means it's a positive axis. Current is leading the voltage means the direction goes out to be like this. So now you have this phase diagram omega t, and here this is the set. Here I you have, here V, this is I naught, this is V naught, and here you have pi by 2, 90 degree. It makes 90 degree. It is leading. For inductor it was lagging, for this it is leading. So this is the phasor diagram for the alternating voltage applied to a capacitor, which is said to be an important concept. So these are the concepts of the applied voltage by which we are checking out to the current. I is equal to I naught sine omega t plus pi by 2 plus pi by 2, positive of the pi by 2, which means to say that it is leading at what degrees? 90 degrees. Having all this, that is resistance, inductance as well as capacitance, behavior with respect to the alternating voltage, we are getting on to a new concept called as, that is applied voltage to series RLC circuit, or it is also called as LCR. Both are one and the same, which consists of resistor, inductor as well as capacitors, which is connected in series to all together, and finally it is connected to the alternating source. So having all this, we will have to get up capacitive reactance. We got inductor. In case of inductor, we got inductive reactance. Similarly, in case of capacitor, we need to get the capacitive reactance. How is that? You know, you have I is equal to V naught C into omega. So we know that V is equal to I into R. R is the resistance. So V by I is equal to R, which resistance is the one which gives opposition to the flow of current. This we have studied in case of non-alternating concepts and all, right? So here we have V by I. So V naught by I naught is equal to 1 by C omega. 1 by C omega is known as the capacitive reactance, which is given by XC. Okay. So according to this concept, XC is equal to 1 by C omega is the capacitive reactance. So for this we have one definition, that is called as capacitive reactance, which means to say that effective opposition offered by the capacitor, because in non-alternating current concepts and all, you have V is equal to I into R. So V by I is equal to R. What is the behavior of the resistance? It is giving the opposition to the flow of current. Similarly, in case of AC, so AC current, what do we have? In the sense, V naught is equal to I naught into C, and omega comes out here. So we have V naught divided by I naught is equal to 1 by omega C. 1 by omega C, this acts as same like resistance R, because of which we call this as capacitive reactance, and capacitive reactance is given by X and C. So this is all about the capacitive reactance formula. Next we are getting on to the inductors, resistance as well as the capacitor LCR circuit. Alternating voltage applied to LCR circuit, which is one of the most important derivation which is for 5 marks. So you have to be very attentive when I'm explaining regarding this concept. That is, for this LCR circuit we connect in series, that is resistance. Second thing is inductor as well as capacitor, RLC circuit or LCR circuit is what we call this. What happens when we apply the alternating voltage to it? So it is connected to a source which is known as AC source, for which how will it give the alternating voltage? And we actually know that V is equal to V naught sine omega t is the first main equation what we plot once we get to know that the alternating voltage is there. Whenever there is alternating current, which is alternating source which is attached to any of the circuits, we just consider the instantaneous value. So here usually for all the derivations we consider the instantaneous potential values. V is equal to V naught sine omega t. For this, what is the next step we are going to do is, so we know that according to Ohm's law we have V is equal to I into R. So V R, the voltage across the resistance R is VR, the voltage across the inductance is VL, and the voltage across the capacitance is VC. Okay, so this is across the capacitors. The total voltage can be given as V naught over here, which is the peak voltage which is present over here, for which you have VR. For resistance, when the voltage is applied to a resistance, what is VR? That is I naught into R. In case of voltage across the inductance, it is I naught into XL. In case of capacitor, I naught into XC. So this is the initial things what we have with respect to the voltage. Next, we have a representation. By having the representation with respect to this applied voltage to resistance, capacitance and inductance, we next follow with the other steps. That is, we have something like phasor diagram. We have a representation which resembles the phasor diagram, okay, which is taken as initial condition. From this diagram itself, we can derive the rest of the things. That is, you have phasor over here. So now it is like phase diagram what we are drawing. So now first of all, we consider what happens when an alternating source is applied to a resistor. First, the condition goes only with the resistor concept. One by one, we are going to split and then give the phasor over here, okay. So whenever an alternating source is applied to a resistor, what happens? There exists something which is known as a current I, okay, for which the voltage VR is in phase. So I as well as VR both are in phase with each other is the concept what we have studied under the phasor, right? Under the alternating voltage which is applied to a resistor. Next we are going on to alternating voltage applied to a inductor. When we consider inductor case, here it is like the voltage leads but the current lags. Understood? It is like the voltage leads current by your leading voltage than that of the current. The current is the one which leads the voltage by 90 degree, for which it is shown in 90 degree. It is leading x-axis, y-axis, and it is 90 degree what we have. So here it is VL. Similarly, the current lags the voltage with respect to capacitor. Whenever the alternating voltage is applied to a capacitor, the voltage is lagged behind but the current is forward. It is moving forward, that is plus 90 degree ahead than that of the voltage. That is why we draw this in negative axis. So we have VC. So if we are considering this vector, or else this vector and this vector, either of the two vectors can be considered, okay? Both also it's one and the same, and both also it's right. Format is the same, okay? Both also goes with the parallelogram law of vector addition, for which you have a diagonal what you draw, and then you can just fix both all together. Okay, so even if you take just these things and go with the Pythagoras theorem, that is also right. Even if you take parallelogram law of vector addition also, that is also right. For both the cases also you can go with this. Okay, next you have, just give the names as this is E, this is A, and this is D. Now go with the Pythagoras theorem. So here you have diagonal is OE square, or the resultant, square of the resultant, and sum of squaring of other two sides will be, you have AE square and plus you have OA square. Okay, so now OE square is the V naught is what we are dealing with, that is the peak value. AE square, which means OD square, both are one and the same, and the value of this is, from VC you will minus VL. This line you are subtracting the voltage of this inductor and then you are giving, so it is VC minus VL the whole square plus OA, OA square is nothing but VR. So you have VR. V naught is equal to VR square plus VC minus VL the whole square, VC minus VL the whole square. For your convenient, you can just change the things and you can write. So V naught is equal to, what is VR? VR is I square into R square plus what is VL? VL and VC, you have the equations here. You have I naught. So this will also be I naught into XC minus I naught into XL the whole square. So the common what we can take out from all this equation is I naught square. So V naught is equal to I naught square, taking common out, we have R square plus XC minus XL the whole square is what we have. So this is also square because we are squaring this. Okay, so now V naught is equal to root of I naught square is nothing but I naught. You're taking the square over here and applying root to R square plus XC minus XL the whole square is what we are doing. So V naught divided by I naught is equal to root of R square plus XC minus XL the whole square. This is of the form V by I is equal to R. So this will be the resistance which is offered, that is opposition offered when the source is connected to RLC circuit, which can be called as V naught by I naught as Z. Therefore, Z is equal to root of R square plus XC minus XL the whole square, and we know that XC is equal to 1 by omega C and XL is equal to omega L. Having these concepts, you can either apply to this and then perform the equations. So that's all about the alternating voltage applied to a series LCR circuit, where we have this set of equation V naught is equal to I naught of the impedance. Okay, so Z is nothing but it is also known as impedance. Impedance means it is the opposition offered for the flow of charges in the alternating current is what we study over here. Suppose if you want to check the phase difference, you can go with tan phi is equal to, tan theta is equal to opposite by adjacent. Opposite you have AE, so it is VC minus VL divided by adjacent is OA and it is nothing but VR, which is equal to I naught into XC minus I naught into XL divided by I naught into R. We end up with XC minus XL divided by R because taking I naught common outside, it just cancels out. So tan phi is equal to this equation. So phi is equal to the tan inverse of XC minus XL divided by R is the final equation for the phase difference. To find out the phase difference, you have that equation. That's all about the alternating voltage applied to a series LCR circuit. Under this, we just have to give the waveform diagram as well as the phasor diagram. To give the waveform diagram, we have here a wave nature, for which we will have to give how exactly the current is following. So the current representation turns out to be like this. So it is pi by 2, here it is 3 pi by 2, 5 pi by 2. So this is voltage, this is current, the phasor difference. This will be the phase difference between the voltage as well as current. So that's all about the waveform diagram. Now the phasor diagram, we just gave it as the phase with respect to its direction. So we have this as phi and this as omega t, this is V and this is I. So this is the phasor diagram what we are giving for the series LCR circuit, or it is also called as RLC circuit. So that's all about the series LCR circuit applied voltage, which is very important for 5 marks up till here. Okay, so next we are dealing with impedance. What is meant by impedance? Which means to say that it is represented by Z. Z is equal to root of R square plus XC minus XL, the whole square is the formula what we had studied, which means to say that it is the effective opposition which is offered by the circuit to the alternating current through it, which is flowing through it. This is the opposition which is offered. Having this impedance, we also have something called as admittance, which means to say that it is reciprocal of impedance, which means to say impedance behaves like the resistance in the non-alternating current. Similarly, admittance behaves like a conductance. Conductance is the reciprocal of the resistance. Similar way, admittance means it's a reciprocal of the impedance is what we actually study over here. And you also have susceptance, and susceptance is nothing but the reciprocal of the reactance. Reciprocal of the reactance. In case of reactance, you have inductive reactance, capacitive reactance, all these things, right? It comes under reciprocal of those reactance will be also called as susceptance. So in today's class, we have studied about the applied voltage to a capacitor, applied voltage to a RLC circuit, as well as its respective waveform diagrams and phasor diagrams with respect to what is meant by capacitive reactance and what is meant by impedance. All these things has been studied today. Let us all meet in our next upcoming sessions. Until then, have a good day. Thank you.